Using the periodic table. The periodic table is a powerful tool for chemists. The table is organized on the basis of the atomic structures of elements. In this section, we will examine some of those properties whose variation depends on their electron configuration. These properties should be closely related to their position on the periodic table. The elements do not have the properties because of their positions on the table, but rather both the position and the properties arise from the electron configurations of the atoms. So the periodic table has so much information contained in its organization that it will become your valuable resource in our course. So we want to talk first about how the periodic table is arranged. And we deal with what's called the periodic law. And the periodic law says that when elements are arranged by their atomic number, there is a periodic repetition in their physical and chemical properties. In other words, the properties of elements are based off of their atomic numbers. So when we deal with the periodic table, it's arranged by horizontal rows and vertical columns. So our horizontal rows are referred to as periods. And there are 7 periods on the periodic table. And the periods tell us how many energy levels a particular atom has. Vertical columns are referred to as groups, and sometimes they're also called families. And when an element is in a particular vertical column or group, it shows us how many valence electrons there are. And remember that valence electrons, again, are the electrons in the outermost energy level. And elements in a particular group or family have similar physical or chemical properties because they have the same number of valence electrons. So let's do a quick review of the periodic table. Again, we've got the horizontal rows, which are our periods. We've got the vertical columns, which are our groups. And some of our vertical columns have particular names. Group 1 are called our alkali metals. Group 2 are alkaline earth metals. The middle block is called our transition metals. Group 7 are referred to as your halogens, and Group 8 are your noble gases. And along the bottom we have the lanthanoid and the actinoid series. Another thing we should remember about the periodic table is that we have a staircase on the right side of the periodic table, which separates the metals from the nonmetals. The metals are to the left of the staircase. They tend to lose electrons in order to become stable and form positive ions or cations. To the right of our staircase are our nonmetals. Nonmetals tend to gain electrons in order to become stable and form negative ions or anions. And along that staircase are what we refer to as metalloids. And metalloids can act like metals and lose electrons, or act like nonmetals and gain electrons, depending on what they're reacting with. We also know that there are arrangements for charge on the periodic table. Elements in group 1 form a +1 charge, elements in group 2 form a +2 charge, elements in group 3 form a +3 charge, elements in group 8 don't form ions, elements in group 7 form ions with a -1, 6 with a -2, and 5 with a -3. Now, when we deal with periodic trends, we've already learned one periodic trend: the way electrons are organized in atoms. If we look at the periodic table, we can see that there is a periodic trend with respect to electron configuration. If an element is in a particular period, it designates the number of energy levels. So if we were to look at hydrogen and helium, they're both in the first period and they have 1 energy level. If we were to look at beryllium, lithium, and all the way over to neon, they're in the second period and they have 2 energy levels. If we look at sodium through argon, they're in the third period and they have 3 energy levels. If we look at the group or family that an element belongs to, it corresponds to the number of valence electrons. So if we look at hydrogen, lithium, and sodium as examples, they have 1 valence electron. Beryllium and magnesium have 2. Boron and aluminum have 2 s electrons plus 1 p electron, or 3. Carbon has 4, nitrogen has 5, 6, 7, and 8 going across the periodic table. and that corresponds to the charges on their ions as well. Next, we want to deal with what's called our effective charge. And when we talk about electrons, electrons are bound to the nucleus because the nucleus has a positive charge. And the positive charge in the nucleus is due to the number of protons that are in the nucleus, or the atomic number, which is our letter Z. So we assume that the electrons are bound by a positive charge, Z, or the number of protons that are in the nucleus. But there's an effective charge that the electrons feel, which is going to be less than the charge on the nucleus. The effective charge, or our Z effective, represents the net effect of the attraction of the nuclear charge and the repulsion of the other electrons between the nucleus and the valence electrons. An electron closer to the nucleus would feel more of a positive charge, whereas electrons farther away would feel less of that positive charge. And we also have what's called shielding. And shielding deals with the inner electrons kind of running interference between the positive nucleus and the outer electrons. So shielding is the protection by the inner electrons so that the outer electrons do not feel the full nuclear charge. When we talk about the way that electrons fill orbitals, shielding helps us to explain why the orbitals are filled in the order that they are. The lower the energy orbital, the first it gets filled with electrons. So the orbitals to the inside of other orbitals do a good job of shielding the outer electrons. If we talk about polyelectronic models, we're dealing with atoms that have more than one electron. And the energy required to remove an electron from an atom depends on two factors. Our first factor is the effective nuclear charge. In other words, the combination of the attractive force of the protons in the nucleus and the shielding effect of the inner electrons. And our second factor is the average distance the electrons are from the nucleus. The farther the electrons are from the nucleus, the less of an attractive force they're going to feel. So let's talk about atomic radius and the trend on the periodic table for atomic radius. Atomic radius is half the distance between the nuclei of two atoms. It's kind of like the radius of a circle in geometry. And when we look, we have a trend for atomic radius. Here we have a graph that has atomic number along the x-axis and the radius along the y-axis. And what we should notice is as we go across a particular period, our atomic radius decreases. So if we were to look at the yellow dots as an example, that's going across period 2, or the red dots, that's going across period 3, and so forth. If we were to look going down a group, our atomic radius increases. As an example, if we look at the dot at the top of each of those trends, we're looking at the alkali metal group. So when we look at the periodic table and we see how the atomic radius is arranged, we see that as we go down a group, the size gets bigger, and as we go across a period, the size gets. Now the reason for that is as we go down a group, we're adding more and more energy levels, which is going to increase our radius. As we go across a period, we're adding more and more protons to the nucleus, but we're adding electrons to the same energy level outside the nucleus. So the effective charge increases because our protons increase, but our shielding stays about the same, so our electrons get drawn closer into the nucleus. So our radius increases as we go down a group and decreases as we go across a period. The next trend we want to deal with is what we call ionization energy. And ionization energy is the energy required to remove an electron from an atom. And again, we've got a trend that we see going across the periodic table for ionization energy. And for this, we're looking at what we call our first ionization energy, or the energy to remove the first electron from an atom. If we go across a period, we're going to notice that the ionization energy increases. So if we were to look at the two black dots, we're looking at hydrogen and helium. If we look at the yellow dots, we're looking at our second period. The red dots, we're looking at our third period, and so forth across. So we see that our ionization energy is increasing as we go across a period. If we go down a group, we're going to see that the ionization energy decreases. As an example, if we were to look at the dots at the top of each of those trends, we're looking at an element in the same group, and we see that that trend is decreasing. So ionization energy is the energy required to remove an electron from an atom. It's easier to remove electrons from group 1 than from group 8. And we know that because group 1 elements tend to lose one electron, but group 8 electrons hold on to all of their electrons. It's easier to remove an electron that's farther away from the nucleus, which are elements towards the bottom of a group. So again, if we look at the general trend for ionization energy, as we go down a group, ionization energy generally decreases. As we go across a period, ionization energy generally increases. So as we go across a period from left to right, the first ionization energy increases. So why? Electrons added in the same principal quantum level, or the same energy level, do not completely shield the increasing nuclear charge. Therefore, the electrons are held more tightly by the nucleus as we go across a period. Now, there are some exceptions. Like if we were to look at nitrogen and oxygen, we would expect that the ionization energy would be increasing as we go from nitrogen to oxygen, but in reality, it decreases just a little bit. And if we look at the electron configuration, we can explain that. For nitrogen, we've got 1s2, 2s2, 2p3. So in that 2p3, we've got one electron in each orbital. If we look at oxygen, we have 1s2, 2s2, 2p4. So we're going to have 4 electrons in the p orbital of our second energy level, 1 singly in each of the orbitals, and then there's going to be a pairing up in the first orbital. And those electrons are going to be repelling each other, so we're going to have an easier time removing that 1 electron from oxygen than from nitrogen. To continue the periodic trends, we're going to go on to our second video.